Hello everybody, this is an audio lecture for visually impaired students, and in this audio lecture I am going to read the chapter NITROPRAFINS and Aromatic Nitro Compounds from the book Organic Chemistry Volume 1, The Fundamental Principles, written by I.L. Finar. So this is our chapter nitroparaffins. Firstly, I am going to start the nomenclature regarding the nitroparaffins. The nitroparaffins are named as the nitro derivative of corresponding paraffins. The position of nitro groups being indicated by the numbers. For example, 1 nitromethane. Second example is 2 nitropropane, and third example is 2,4 dinitrohexane. As you can see in these examples, all the nitro groups are indicated by their positions. Now I am going to read the next paragraph. The nitroparaffins, the structure of which is RNO2, are isomeric with the alkyl nitrites, that is RONO. The evidence that may be adduced for these respective formulae is to be found in the study of reactions of these two groups of compounds. The reactions of nitrates have already been discussed, and those of the nitroparaffins are discussed below. It is, however, worthwhile at this stage to mention the reaction which most clearly indicates their respective structures with reduction. When alkyl nitrites are reduced by nascent hydrogen and alcohol, and ammonia or hydroxyl amines are formed. This shows that alkyl group is in nitrates is attached to an oxygen atom. As in this reaction, we can clearly see that when we reduce the alkyl nitrate, then our product alcohol and ammonia are formed over here. On the other hand, when nitroparaffins are reduced, a primary amine is formed. This shows that alkyl group is attached to the nitrogen atom, since the structure of a primary amine is known to be RNH2. From its method of preparation, we can clearly see in this reaction that when we heat the nitroparaffins in the presence of any kind of reducing agent, or we can say we do the process of reduction, then it undergoes reduction and reduced to form primary amines. The structure of nitro compound was originally written that R single bond N double bond oxygen and one coordinate bond with another oxygen atom, but work on dipole moments indicates that they are resonance hybrids. For most of the purposes, however, the original formula, that is R single bond N double bond oxygen and coordinate bond with oxygen, or the non-committal formula, that is RNO2, is satisfactory. From the molecular orbital point of view, the nitro group is conjugated and the delocalization of bond increases its stability. The two oxygen atoms are equivalent as like the carboxylate anion, and we can clearly see in this slide that both the oxygen atom containing minus half formal charge. It shows that both the oxygen symmetrically disperses the negative charge on it. Now we will talk about the general methods of preparation. First method is by heating an alkyl halide with silver nitrite in aqueous ethanolic solution. This method is only useful for preparation of nitroparaffins with secondary halides, and yield is about 15%, and with tertiary halides 0 to 5%. The yield of a nitrite increases from primary to tertiary halide. Kornbluh et al. Have now described a simple new synthesis of primary secondary nitro compounds. These authors have shown that, contrary to general opinion, sodium nitrite react with alkyl halide to give good yield of nitroparaffin, that is 55 to 62%, together with alkyl nitrites 25 to 33%. The success of reaction depends on the use of dimethylformamide as a solvent, and the addition of urea increases the solubility of sodium nitrite. Alkyl bromides and iodides are most satisfactory. The chlorides react too slowly to be useful. Second is nitroethane may be prepared by boiling an aqueous solution of sodium nitrite with halogenoacetic acid. So in this reaction here we have any kind halogenoacetic acid, and when we heat it with sodium nitrite, our required product, that is nitromethane with yield 35 to 38%, is obtained over here. This method has no value of preparing higher nitroparaffins. The ready decarboxylation of intermediate nitroacetic acid may be explained on the assumptions that electron attracting nitro groups facilitates the loss of carbon dioxide. Third, until recently, the preparation of nitro compounds by direct nitration was of academic interest only, but mainly from the work Hess and his co-workers. Direct nitration is now an important industrial process. Two techniques have been evolved: liquid phase nitration and vapor phase nitration. First technique is vapor phase liquid phase nitration. In liquid phase nitration, the hydrocarbon is heated with concentrated HNO3, basically nitric acid, under the pressure at 140 degrees Celsius temperature. Nitration under these conditions is always slow and large amount of polynitro compounds is produced. It is interesting to note that a reaction of it is very interesting to note that a mixture of nitric and sulfuric acids is not suitable for nitrating paraffins, as like in aromatic hydrocarbons. In vapor phase nitration, the hydrocarbon is heated with nitric acid or it's with oxide of nitrogen at the temperature 150 to 475 degrees Celsius. Each hydrocarbon has its optimum temperature. Example, if we take the N-propane and we heat it with a HNO3, basically nitric acid, at the temperature 400 degrees Celsius, then there are different kind of products are obtained, like 1 nitropropane, 2 nitropropane, 1 nitroethane and nitromethane also. Vapor phase nitration is more satisfactory than liquid phase nitration. Hash and Sester have formulated general rules for vapor phase nitration of paraffins and cycloparaffins. First rule is polynitro compounds are formed only from paraffins of fairly high molecular weight. Second is any hydrogen atom in hydrocarbon is capable of replacement by nitro group, and the ease of replacement is tertiary hydrogen, secondary hydrogen and primary hydrogen. As the temperature rises, however, the ease of replacement tends to become equal. Third is any alkyl group present in the paraffin can be replaced by a nitro group, that is chain fission takes place. Example, isopentane yield 9 nitroparaffins. The fission reaction increases as the temperature rises. Fourth is oxidation always accompanies nitration, resulting in the formation of nitro compound and a mixture of acids, aldehyde, ketones, alcohols, nitriles, nitroso compounds, nitroolefins, polymers, carbon monoxide and carbon dioxide. Catalysts such as copper, iron, platinum oxide, etc. accelerated oxidation rather than nitration. Fourth, another recent method of preparing nitro compound is the hydrolysis of alpha nitroolefins with water, acid or alkali. This is the fourth method of preparation of nitro compounds, or we can say nitroparaffins. So in this example here we can take 2 methyl 1 nitroprop 1 ene, which is the simple alpha nitroolefin olefins. When we hydrolyze this alpha nitroolefin, which is particularly a compound named 2 methyl 1 nitroprop 1 ene, gives acetone and nitromethane with almost quantitative yield. Fifth method, Kornblum et al. Have introduced a practical synthesis of tertiary nitro compound by oxidation of tertiary carbonamines with potassium permanganate. So in this reaction here we have a tertiary carbonamines. So when it undergoes oxidation with KMnO4, that is potassium permanganate, it gives a 70 to 80% yield of a tertiary nitro compound, or we can say tertiary nitroparaffins. Now we will talk about the general properties of nitroparaffins. The nitroparaffins are colorless when pure, pleasant smelling liquids which are sparingly soluble in water. Most of them can be distilled at atmospheric pressure. The nitroparaffins in commercial use at the moment are the lowest four member of the series: nitromethane, nitroethane and 1,2-nitropropane. These are prepared by vapor phase nitration of propane and are used as solvent for oils, fats, cellulose, esters, resins and dyes. Now we will talk about the reactions of nitroparaffins. First is nitroparaffins are reduced in acid solution to primary amines. Catalytic reduction also produces a primary amine. The yield with Raney nickel catalysts being 90 to 100% when the reduction is carried out in neutral solution, example with zinc dust and ammonium chloride solution, nitro compound are converted into hydroxyl amines derivative. So here in both reactions we can clearly see that if we take nitro compound, or we can say nitroparaffin, in the presence of zinc in the presence of ammonium chloride, then it will provide us a hydroxyl amine. When stannous chloride and hydrochloric acid are used as reducing agent, nitro compounds are converted into a mixture of hydroxyl amine derivative and oximes. Since hydroxyl amine can give rise to type of derivatives, example RNHOH and NH2OR, it is necessary to distinguish one from other. A common method is named that former as N-alkyl hydroxyl amine and the latter is O-alkyl hydroxyl amine, the capital letter N and O respectively indicating where the alkyl group is attached in the molecule. Second, the primary nitro compounds are hydrolyzed by boiling hydrochloric acid or by 85% sulfuric acid to carboxylic acid and the hydroxyl amine. This reaction is now used for manufacturing hydroxyl amine and may become a commercial source of propionic acid using 1-nitropropane. Secondary nitro compounds are hydrolyzed by boiling hydrochloric acid to ketone and nitrous acid. Tertiary nitro compounds are generally unaffected by hydrochloric acid. Third is primary and secondary nitro compounds, that is those containing alpha hydrogen atoms, are acidic in character due to the tautomerism. The nitro group is a very strong negative group and contain multiple bonds. As the nitroform structure, one is often called pseudonitric pseudoacid form. Second is known as the aciform or nitronic form. This is an example of a triad system, the nitro-acid-nitro system. The equilibrium is almost completely on the left hand side, and this may be due to nitroform being stabilized by resonance of the nitro group. These nitronic acids do not dissolve in aqueous sodium carbonate but do in aqueous sodium hydroxide, which disturbs the nitro-acid-nitro equilibrium by removing the latter form. Thus, nitro compounds behave as acid in presence of strong alkalis but not in their absence, hence they are said to be new pseudoacids. These sodium compounds are true salts, that is they exist as ions R2C, R2, R2C, NO2 minus and Na positive. When the sodium salt is acidified at low temperature, there is not only an intermediate separation of oily drops of nitroform. On standing, however, the acidified solution slowly deposits oily drops due to the slow tautomeric change of nitronic acid into the nitro compound. Furthermore, when the sodium salt is carefully neutralized with hydrochloric acid, the resulting solution has a conductivity which is greater than the calculated for sodium chloride content. Hence, in addition to the sodium and the chloride ion, there must be present in other ions which are must be those from the nitronic acid. Thus, the following changes probably takes place. This is evidence for existence of nitronic acid. Actually, Henschel and Schalje isolated both forms of phenyl nitromethane, thus confirming the existence of nitroacinitro-tautomeric system. When the sodium salt solution of nitronic acid is acidified with 50% sulfuric acid at room temperature, an aldehyde from a primary nitro compound and a ketone from a secondary nitro compound is obtained. Example, R dash is either an alkyl radical or an hydrogen atom. When treated with stannous chloride, the hydrochloric acid and the sodium salt of nitronic acid is reduced to aldoximes or ketoximes. These oximes are readily converted into parent carbonyl compound by steam distillation or by direct hydrolysis with acid. Fourth is primary and secondary nitro compounds are readily halogenated in alkaline solution in the alpha positions only. Primary nitro compounds can form the mono and dibromo derivatives, where the secondary form only the monobromo derivative. Nitroethane is exceptional in that it can form the tribromo derivative, that is chloropicrin is manufactured by reaction between nitromethane and chlorine and sodium hydroxide. When liquid or gaseous nitro compounds are treated with halogens in the absence of alkali, indiscriminate substitution takes place, resulting in the formation of alpha, beta, gamma halogeno compounds. Example, if we have nitroethane and we react it with chlorine Cl2 gas, then there are two kinds of different products are formed, like 2-chloronitroethane and 1-chloronitroethane. Fifth is nitro compound reacts with nitrous acid and the product from depending on the nature of the alkyl group. Primary nitro compounds form nitrolic acids. These are crystalline substances which dissolve in sodium hydroxide to give red solutions. Secondary nitro compound forms pseudonitrols, or we can, and the cross nitrols. These are colorless crystalline substances which dissolve in sodium hydroxide to give blue colors. The blue color is probably due to the presence of nitroso group, as we can see in this reaction. Tertiary nitro compounds do not react with nitrous acid since they have no alpha halogen atom. These reactions with nitrous acids are the basis of red, white and blue test for nature of monohydric alcohols, that is Victor-Mayer test. The alcohol under investigation is treated as follows. Firstly, our alcohol is converted into our alkyl halide using PBr3 or any kind of reagent which converted into alkyl halide. Then further we reacted with AgONO, that is silver nitrite, and we converted into nitro compound. The nitro compound is now treated with alkaline solution of sodium nitrite acidified with hydrochloric acid and finally made alkaline with sodium hydroxide. The development of a red color indicates a primary alcohol, blue color a secondary, and the solution remaining colorless white a tertiary alcohol. This is a test now only historically important. Sixth, owing to the presence of active alpha hydrogen atom, primary and secondary nitro compounds undergo condensation with aldehyde. Examples, nitromethane condenses with benzaldehyde in the presence of ethanolic potassium hydroxide to form omega nitrostyrene. Second is nitroethane condenses with formaldehyde in the presence of aqueous potassium hydrogen carbonate to form a bis hydroxymethyl compound, that is 2-methyl-2-nitropropane 1,3 diol. The condensations are similar to the aldol condensation, the active methylene or methylene group being produced by adjacent nitro group. The sodium salt of nitronic acids condense with alpha beta unsaturated ketones. Example, with acetyl oxide nitromethane forms 4,4-dimethyl 5-nitropentane 2-one. So here we can see in this reaction, primary and secondary nitro compounds also undergo the Mannich reactions. This is due to the condensation between the formaldehyde, ammonia and or a primary or a secondary amine, preferably as a hydrochloride. hydrochloride and a compound containing least one active hydrogen. In this reaction, the hydrogen atom is replaced by amino methyl group or substituted amino methyl group. The Monic reactions offers a means of preparing a large variety of compounds, example nitroamines, diamines, etc. So here our next chapter is aromatic nitro compounds. Our next topic that we will discuss in this section, that is aromatic nitro compounds. So the aromatic nitro compounds are almost invariably prepared by direct nitration using one of the following reagents, that is concentrated nitric acid, density is about 1.5, fumic nitric acid 6 to 12%, nitrogen dioxide, mixed acids. This is the mixture of nitric acid that is concentrated or fuming and various amounts of concentrated sulfuric acid, sometimes fuming sulfuric acid is used. Mixed acid is by far the most important nitrating agent. Occasionally other acid besides sulfuric acids are used. Examples: glacial acetic acid. Boron trifluoride is a very effective catalyst for nitration. One equivalent of catalyst must be used. The yield are better and the products purer than by above methods. Furthermore, boron trifluoride is particularly useful for nitrating compounds containing a negative group. Olaha et al. Have shown that nitronium tetrafluoroborate, a stable compound, is useful nitrating agent, as we can see in this reaction. This is a method of nitration gives direct preparative proof of electrophilic character of nitration through the nitronium cation. Fourth, acetyl nitrate CH3COONO2 is a useful as a nitrating agent in certain cases since it introduces a nitro group into the ortho position and produces almost only one monoderivative. Acetyl nitrate, however, is somewhat dangerous to use since it tends to explode when heated. The nitrating agent used when depends on the nature of compound to be nitrated and the object in view, that is the introduction of one or more nitro groups. In any case, whichever reagent is used, it is usually difficult to stop the nitration process at one nitro group except with acetyl nitrite. As an outcome of a great deal of experimental work, it has been shown that nitration with mixed acid, that is nitration in sulfuric acid, is due to some substance produced from the nitric acid and not the nitric acid itself. According to Bennett et al. And the Inglot et al. 1946, the active nitrating agents is nitronium cation, that is NO2 plus, which they believe is formed as follows. The evidence for existence of nitronium cation is shown by electrolysis experiment. Example, that it has been found that nitric acid in oleum migrates to the cathode by cryoscopic experiments in which it has been shown that the Van 't Hoff factor, that is I, is 4. This value satisfy the equation given above, that is HNO3 plus 2 equivalents of H2SO4 gives nitronium ion H3O plus and HSO4 negative. By the isolation of salts of nitronium ion, example nitronium perchlorate, that is NO2 positive ClO4 negative, and the nitronium tetrafluoroborate, that is NO2 plus and BF4 negative. Fourth technique is by spectroscopic analysis, which has shown in existence of nitronium ion. Nitration with mixed acids thus possibly proceeds as follows. Nitration in concentrated aqueous nitric acid and in organic solvent is also believed to via a nitronium ion. On the other hand, in more dilute nitric acid solution, it is probably that the nitroacidium cation that involved in nitration. The catalytical effect of boron trifluoride is believed to be due to the formation of nitronium ion. According to Longmans et al., the active species which acetyl nitrate and other organic nitrates is dinitrogen pentoxide. General properties of nitro compound. Most of the nitro compounds are yellow crystalline solid and few including nitrobenzene are yellow liquid. Many are steam volatile and except for a few mononitro derivatives cannot be distilled under atmospheric pressure because when strongly heated they decompose often with explosive violence. All the nitro compounds are denser than water in which they are insoluble. They are, however, readily soluble in organic solvents. The nitro group is firmly attached to the nucleus and may be replaced only under certain conditions. Nitro compounds form addition products with many aromatic compounds. Their most important reaction is their reduction by various reducing agents. Nitrobenzene oil of myrrhine, that is C6H5NO2, may be prepared by the action of cold mixed acid on benzene and then warming to complete the reaction. It is a pale yellow, has boiling point 211 degrees Celsius with a small smell like benzaldehyde. It is almost insoluble in water but is steam volatile. Its vapor is poisonous. It is used for scenting cheap soaps, in the manufacture of floor polishes, aniline, benzidine, and some azo-dyes, etc. It is used as solvent and is used occasionally as an oxidizing agent in organic chemistry, example in preparation of quinoline. When heated with solid potassium hydroxide, nitrobenzene produces a mixture of ortho and para nitrophenols and some azoxybenzene. Dinitrobenzenes. When nitrobenzene is heated with mixed acid, fuming nitric acid, and concentrated sulfuric acid, the main product is metadinitrobenzene. As nitric acids alone may be used to introduce one nitro group, mixed acid must be used to introduce the second nitro group into nitrobenzene. Metadinitrobenzene is a pale yellow solid melting point 90 degrees Celsius, practically insoluble in water but in steam volatile. It may be reduced stepwise, example sodium sulfide to metanitroaniline and then to metaphenylene diamine. The hydrogen atom ortho or orthopara to 2 nitro groups is easily displaced by oxidation but not by substitution. Example, metadinitrobenzene is oxidized by an alkaline solution of potassium ferricyanide, that is K3FeCN6, to a mixture of 2,2-dinitrophenol mainly and 2,4-dinitrophenol mainly and 2,6-dinitrophenol small amount. Orthodinitrobenzene can be isolated after removing the meta-isomer when the nitrobenzene is nitrated. Nitration of acetanilide gives the mixture of ortho-para-nitroacetanilides. These isomers are separated, each is deacetylated and by replacing the amino group by nitro group. The ortho and para-dinitrobenzenes may be obtained pure. It is necessary to product compounds with hydroxyl or amino groups in the ring since these compounds are very easily oxidized instead of nitrated by nitric acid. An alternative method for preparing ortho and para-dinitrobenzenes is also oxidize the corresponding nitroaniline with Carose acid and then to oxidize the product, the nitro-nitroso derivative, with a mixture of nitric acid and hydrogen peroxide. On the other hand, peroxytrifluoroacetic acid oxidizes the amino group directly to the nitro group. Para-dinitrobenzene may also be prepared by oxidizing para-benzoquinone dioxime with nitric acid. Ortho and para-dinitrobenzenes are colorless solids. Melting point is 118 degrees Celsius and 173 degrees Celsius respectively. They resemble the meta-isomer in many ways but differ in their following respects. First, when ortho and para-dinitrobenzenes are boiled with aqueous sodium hydroxide, one nitro group is replaced by hydroxyl to give corresponding nitrophenol. This reaction is used to separate metadinitrobenzene from its ortho and para isomers in the industrial preparation of metadinitrobenzene. Second, when boiled with ethanolic ammonia and ortho-para-dinitrobenzenes are converted into corresponding nitroanilines and one nitro group being displaced by the amino group. Third, when boiled with methanolic sodium methoxide and ortho-para-dinitrobenzenes are converted into the corresponding nitroanisols, one nitro group being replaced by methoxyl group. These nucleophilic substitutions are characteristics of polynitro compounds in which two nitro groups are in ortho or para position, one nitro group being replaced by a hydroxyl amino or methoxyl group. S-trinitrobenzene may be produced by the nitration of metadinitrobenzene when mixed acid consisting of fuming nitric acid and fumic sulfuric acid. This reaction takes 5 days to complete. It is very difficult to introduce the third nitro group and it is impossible to produce more than 3 nitro groups by direct nitration. A better method of preparing a S-trinitrobenzene is to oxidize 2,4,6-trinitrotoluene and to decarboxylate the trinitrobenzoic acid so produced by heating it in acidic acid solution. It may be also prepared by the removal of chlorine atom in picryl chloride by means the hydrogen iodide generated from sodium iodide and acetic acid in acetone solution. S-trinitrobenzene is a colorless solid melting point 122 degrees Celsius. It forms well-defined addition compound with many aromatic compounds such as hydrocarbon, phenols, etc. Many polynitro compounds form these complexes and the forces that hold the two components together have been the subject of much discussion. It has been suggested that these complexes are charge transfer complexes. The closed aromatic sextet of the nitro compounds forming a pi complex with other component. The stabilization of the complexes depends upon the overlap between the highest filled molecular orbital of donor molecule and lowest unfilled molecular orbital of acceptor molecule. However, there are also complexes which are held together by dipole-dipole interaction, van der Waals forces, etc. The term polarization bonding, first used by McQueen et al. In 1951, has been used by Mulliken 1952 to include both charge transfer bonding and the weaker polar interactions. Well work 1961 from his X-ray analysis work has concluded that a polarization bonding in complex between aromatic molecules results in a characteristic plane-to-plane structure in the crystal lattice and B where charge transfer forces predominant and the relatively orientations and the position of components are found to be such as allow to the maximum degree of overlap between their molecular pi orbitals. When three nitro groups are present in the ring as in S-trinitrobenzene, one may be removed by the reagent which attack the ortho-para-dinitro compound. Example, when heated with methanolic sodium methoxide, S-trinitrobenzene forms 3,5-dinitro-anisole. Benzene may be oxidized and the nitrated simultaneously to dinitrophenol and picric acid by mercuric nitrate in the nitric acid solution. Nitrotoluenes. Benzene homologues are readily nitrated than benzene itself due to the activating effect of alkyl group. When nitrated with mixed acid, toluene forms a mixture of ortho and para toluenes. These isomers may readily be separated by fractional distillation under reduced pressure. Ortho isomer melting point -4 degrees Celsius, boiling point 222 degrees Celsius, para isomer melting point 54 degrees Celsius and boiling point 238 degrees Celsius. A larger yield of orthonitrotoluene may be obtained by nitrating toluene with acetyl nitrate. Metanitrotoluene melting point 16 degrees Celsius, boiling point 227 degrees Celsius may be prepared by reducing the para isomer, acetylating the para-toluidine nitrating the acetyl derivative, deacetylating, and the replacing the amino group by hydrogen. All nitrotoluenes may be reduced to corresponding toluenes. A very interesting oxidizing effect of nitro group is the internal oxidation of orthonitrotoluene to orthoaminobenzoic acid when heated with ethanolic sodium hydroxide. Dinitrotoluenes. Nitration of any nitrotoluenes gives a mixture of 2,4 and 2,6 dinitrotoluenes. 2,4,6 trinitrotoluene TNT melting point 81 degrees Celsius may be prepared by the nitrating toluene and mixed with acid consisting of fuming nitric and fumic sulfuric acid. The reaction takes place far more readily than with benzene because the activation of ring by methyl group. Trinitrotoluene is used as an explosive mixed with ammonium nitrate. It forms the explosive ametol. Artificial musks. Polynitro derivatives of benzene containing a tertiary butyl group poses a odor resembling musk and are used in perfumery. For example, toluene musk, musk ambrate, and musk ketones. Halogeno-nitrobenzenes. Nitration of phenyl halides produces a mixture of ortho and para-halogeno nitrobenzenes. These may be separated by freezing and filtration. The para isomer having the higher melting point, the halogen atom ortho and para to a nitro group, is fairly reactive and is replaced when heated with alkali, ethanolic ammonia, etc. to form respectively nitrophenols, nitroanilenes, etc. Smith et al. Have shown that the halogen atom in halogeno-nitro compounds may be removed by heating with copper powder and benzoic acid. Chlorine and bromine may be removed when ortho or para to a nitro group. Iodine is removed from any position and fluorine not at all. Example: here we have a orthobromonitro compound. When we heat it with copper powder in the presence of benzoic acid, it will reduced into it will converted into nitrobenzene. Basically, Br bromine group is removed. Similarly, if we have iodine, then it will if we have iodine then similarly it is removed from that position and converted into nitrobenzene. When two nitro groups are present in ortho and para positions with respect to the halogen atom is more reactive, and when three nitro groups are present in the para and two ortho positions, the halogen atom is so reactive that it can be replaced by hydroxyl merely by warming with water. Example: picryl chloride forms picric acid. So here in this example there is picryl chloride, which is simply on hydrolysis give and converted into picric acid. It is also interesting to note that the fluorine atom in 1-fluoro-2,4-dinitrobenzene is strongly activated. This compound condenses with amino group to form a 2,4-dinitrophenyl derivatives. This reaction has been used in protein and peptide studies. A methyl group is also made reactive by nitro group in the ortho and para positions. Example: trinitrotoluene condenses with benzaldehyde in the presence of ethanolic potassium hydroxide to form trinitrostibulene. Halogenation of nitrobenzene produces mainly meta derivatives. A halogen atom meta to a nitro group shows the same unreactivity as the halogen atom in a phenyl halide. Phenyl nitromethane, that is C6H5CH2NO2, may be prepared by heating toluene with dilute nitric acid in sealed tube at 100 degrees Celsius or by heating benzyl chloride with aqueous ethanolic silver nitrate solution. Phenyl nitromethane is best prepared as followed method, which is given in this slide. First is sodiophenyl acetonitroacetonitrile and second is sodium salt of phenyl nitroacetic acid. Phenyl nitromethane behaves as a true primary aliphatic nitro compound. Both the nitro and the acenitro forms have been isolated. Abnormal nitration. When nuclear substituted aromatic compounds are nitrated, there are many cases where an alkyl halogen, alkoxyl, acyl, carboxyl, or sulfonic acid groups is replaced by a nitro group. In some cases, a hydrogen atom in a side chain is replaced by the nitrate group. Generally, abnormal nitration is more likely to occur in nitration of polysubstituted benzene compounds, particularly the polyalkyl benzenes, mono, di, and trialkyl benzenes, where the alkyl group is methyl or ethyl, give the expected nitro compounds. Polyalkyl benzenes containing 3 or more alkyl groups in some cases give normal products, and in other abnormal. Example, phenylmacetylene when nitrated with mixed acid, fuming nitric and sulfuric gives 3,5,6 trinitro 4 ethyl orthoxylene. So this is the final topic of aromatic nitro compounds. Thank you.